Chapter 3. Doing loop. Section 1. Single layer loop. So far, all the code we have written is executed once from top to bottom and then ends. The if statements may cause some code to be skipped and not executed. The overall flow of the program is still from top to bottom, and no code will be executed multiple times. In fact, what computers are best at is repetitive work, that is, to execute the same code over and over. Obviously, we should not copy the code repeatedly, which requires the ability of the program language to loop. Let's calculate the sum of the numbers 1 to 100. Only 2 lines are okay. After the program is executed, the A1 value becomes the answer we want, 50-50. Almost all programming languages use the keyword for loop statements, and SBL is no exception. The for 100 in A2 means that the code block of A2 will be executed 100 times. Here, the code block of A2 has only B2, that is, B2 will be executed 100 times. During execution, the cell value of A2 will start from 1, add 1 after each execution, and finally become 100. A2 cell with 4 is called loop cell. The code block of A2, that is, the code to be repeatedly executed, is called the loop body of A2. A2 itself is also called the loop variable of the loop, and it will change from 1 to the number of cycles. Let's look at this code. We have understood the statement x equals x plus 1 before. A1 equals A1 plus A2 in the loop body is similar, that is, each time we add A2 to the current A1, A2 will increase from 1 to 100, so A1 will add 1, 2, until 100, and the calculation of the sum of 1 to 100 is completed. We can also use this structure to calculate 1 plus 3 plus 5 all the way to 199, that is, the sum of the first 100 odd numbers. This time, it's still to add 100 numbers, so we need to loop 100 times. The loop variable A2 will still change from 1 to 100, but the number to be added is no longer a direct loop variable, and it needs to be calculated through the loop variable, 2 asterisk A2 minus 1. Now we do a slightly more complex operation. According to Taylor formula, add the first 20 terms to calculate the approximate value of the natural logarithm base e. Here, we need to introduce an auxiliary variable b1 to store the factorial value of the nth term, which is also calculated step by step in the loop. Finally, the result is accumulated in A1. Use the expression of A4 to see the difference between the calculated result and the actual value. The function exb1 will calculate the value of e, that is, e to the power of 1. This code cannot loop too many times, because the factorial value of n is going to get very big, and it's going to get out of the range of floating point numbers very quickly. Fibonacci sequence is such a sequence that the first and second terms are all 1. From the third term, each term is equal to the sum of the previous 2 terms, that is, 1, 1, 2, 3, 5, 8, etc. This is a famous rabbit sequence. If you are interested, you can search its origin. I won't repeat it here. Now let's calculate the nth term of the Fibonacci sequence, where n is greater than 2. B1 is the result we need. A2 is the number of terms we want to compute, which is n. The number of loops in a for statement is not always a constant, but can also be a calculation expression A2 minus 2. Because the first 2 terms already exist, we only need to calculate n minus 2 times. There is no loop variable used in this loop body. A3 only controls the number of loops. Calculate the next item in B3, and then fill in A1 and B1 respectively to replace the original items. In this way, for each loop, A1 and B1 are equivalent to moving forward once in the Fibonacci sequence, from the first and second items to the second and third items, and then to the third and fourth items and so on. At the end of the loop, they will become the n-1 and n items, and B1 is the result we need. This code can also be written 1 line less, without the intermediate variable. Debug it and try to find its logic by yourself. We learned the goto statement in the previous section. In fact, we can use goto and if to create the effect of the for statement. For example, in the first example of calculating the sum of the numbers 1 to 100. Here A1 plus equals B1 is equivalent to A1 equals A1 plus B1. Similarly, B1 plus equals 1 is equivalent to B1 equals B1 plus 1. This is a simplified way of writing in C language. This style is retained in SPL. X plus equals Y is equivalent to X equals X plus Y. Similarly, subtraction, multiplication, division can be written like this, but addition is the most commonly used. Using if and goto to create loops, a loop variable needs to be defined artificially. B1 is the loop variable here. First, an initial value of 1 is assigned to the loop variable. Then the if statement is used to judge whether the loop ends or not. If not, the loop body will be executed. After execution, the loop variable will be added by 1, and then goto will be used to jump back. If the loop end condition is true, the if statement will no longer execute the loop body. Obviously, the loop written by the for statement is simpler than the if goto structure, and it is not easy to make mistakes. If the action of adding a loop variable by 1 is omitted accidentally, the loop created by if goto will never end. Moreover, such goto violates the principle of not jumping backward. So we don't usually use if goto to create loops. Section 2. Multilayer loop. Just as if-else may be found in the code block of if and else, there can be for again in the loop body of for, which we call multilayer loop. Narcissus number refers to a 3-digit number that the sum of the cube of each digit is equal to the number itself. Now we want to calculate all Narcissus numbers between 100 and 999. We haven't learned the concept of set yet, and can't save all the Narcissus numbers found in one set. So in cell E5, we use the output function to output the Narcissus numbers, which can be seen in the lower right corner. A new grammatical form, 409, appears in B2 and C3. Usually, the statement for n means that the loop variable will change from 1 to n, but sometimes we want to change the start and end values. We can also write the loop statement as for ab, which means that the loop variable will change from a to b, where a and b are integers. If b is greater than a, the value of loop variable will be a plus 1, until b, and the number of cycles will be b minus a plus 1 in total. If b is less than a, the value of loop variable will be a minus 1, until b, and the number of cycles will be a minus b plus 1 in total. Cell A1, B2, C3 respectively loops through each digit of the 3-digit number. This is code for 3-layer loop. The outermost layer A1 loops through the hundreds digit, the middle layer B2 loops through the tens digit, and the innermost layer C3 loops through units digit. Because there are 10 possibilities for tens digit and units digit from 0 to 9, if it is written as 410, it needs to subtract 1 in the later operation, which is troublesome, so it is easy to write it as 409 directly. In multilayer loop, the complete inner loop will be executed every time the outer loop body is executed. In this way, A1 will loop 9 times and B1 will be executed 9 times. B2 itself will loop 10 times, and C2, as a statement in the loop body of B2, will be executed 9 times 10 times, that is, 90 times. D3 and E3, as statements in the loop body of C3, will be executed 9 times 10 times 10 times, that is, 900 times. The 3-digit number and the sum of cubes of each digit are calculated by D3 and E3 respectively. The calculation of B1, C1, and C2, D2 is to try to make the calculation amount smaller. When the number of units digit changes in a cycle, the number of hundreds and tens is temporarily unchanged, so it is unnecessary to repeat the calculation for the hundreds and tens every time. This is also a matter of attention when coding. The execution times of inner loop body statements may be very many, and a little less computation will reduce the total calculation amount, thus greatly improving the performance of the program. Now you can execute the program by yourself, and check the output at the bottom right, to see which Narcissus numbers are calculated. By the way, we use multiplication when we calculate cubic here, and we also used multiplication to calculate square when we talked about quadratic equation before. Why not use power function directly? Actually, power function can be used when calculating square before, but it can't be used here. Because power function is calculated by exponent and logarithm, it will return a floating point number. But it needs to be compared accurately here, and it is not reliable to use floating point numbers. So we'd rather multiply it 3 times. Also because of this, we should write for 0,9 instead of for 10, otherwise it is a bit troublesome to write multiplying b2 minus 1 3 times. The reason why we didn't use power function to calculate square before is that it is not difficult to write self-multiplication twice, and it will be much slower to calculate with exponent and logarithm, so it is also written as self-multiplication. These are also details that you need pay attention to when programming. This code can also be optimized. If the sum of cubes of each digit is larger than the 3-digit number, it is unnecessary to loop the units digit anymore. Because when the hundreds and tens are unchanged, when the number of units digit is looped to the next, i.e. added by 1, this cube sum will increase by at least 1, and the 3-digit number itself will only increase by 1. Specifically, this cube sum increases by 1 only when the units digit changes from 0 to 1 and increases greater than 1 for any other change. Then, the gap between the 3-digit number and the cube sum cannot be smaller and will be bigger in general, so they cannot be equal. In other words, once we find D3 is less than E3, C3's loop is unnecessary to continue. It is impossible to find a Narcissus number under the condition that A1 and B2 are unchanged. Any further calculation is just a waste of time and calculations. Most programming languages, including SPL, provide break statement to abort the current loop, and the code is rewritten like this. This code has one more line, but the computing performance is much better than before. In fact, the analysis of single digit just now holds true for tens digit because the cube of numbers 0 to 9 must not be less than itself. If C2 is less than D2, then D3 is certainly less than E3. At this time, there is no need to do the third layer loop. The code can be further optimized. The above analysis can be extended to the hundreds digit, but it doesn't make any sense. Please think about the reason here. Now, the optimization of this code is basically over. Section 3. Conditional loop. For n and for ab are both loop with definite number of cycles, but sometimes we don't know how many times to loop. The loop is ended only when a condition is true or not, and the loop body is repeated before that. This kind of loop is called conditional loop. In fact, for n and for ab can also be understood as such a loop, that is, ending the loop when the loop variable exceeds n and b. Exceeding here does not necessarily mean greater than. Conditional loop is a more general form of loop. There is a classical method to calculate the greatest common divisor of two numbers, which is called successive division method. Two positive integers a and b, assuming a is greater than b, replace a with the remainder of a divided by b, now a is less than b, and then replace b with the remainder of b divided by a, and then a is greater than b. Repeat this process until one of a or b is 0, then the other one that is not 0 is the greatest common divisor of the original a and b. Because a and b exchange positions repeatedly to calculate the remainder, it is called successive division method. This is the way Euclid, a Greek geometrician, invented more than 2,000 years ago. Interested readers can prove it by themselves. We use program code to implement it here. Set the original two numbers in the cells A1 and B1. The calculation result will be shown in A1. The code of cell A2 is for B1 greater than 0, for is followed by a Boolean expression. When it calculates true, the loop body will be executed once and then return to A2 to calculate the Boolean expression again. If it is still true, the loop body will be executed again. Until the Boolean expression is evaluated as false, the loop ends. This logic can realize Euclidean division. We don't know how many times to loop, only know that when B1 is 0, the loop can be terminated. Most programming languages have conditional loops, but they usually use while. Words like if, else, for will be used in the program code to represent certain special statements, called reserved words or keywords of the program language. These reserved words are of special significance and cannot be used as identifiers such as variable names. All programming languages have a number of their own reserved words. SPL does not want to have too many reserved words, and it is not ambiguous to use for to represent conditional loop, so it does not retain the more common reserved word, while. Let's do another exercise related to divisor, prime factorization, which is the content of mathematics lesson in primary school. The method is very simple. Given a positive integer n, we divide it by 2. If it is divisible, then we get a factor 2. We divide n by 2 to get a new n, continue to divide it by 2 until it is not divisible by 2. If n becomes 1, it's over. If n is not 1, continue to divide it by 3 and repeat the process, continue to divide n by 4, 5 etc. In the end, n is always changed to 1, and it's over. As we said before, because we haven't learned set yet, we can output the prime factors we find out. Let n fill in cell A1 first. Note that integer division should be used in cell C3, otherwise floating point number will be calculated, and the next A1% B1 cannot continue. This is a two-layer loop code. It can also be written as a single-layer loop. Replace the 4 of cell B2 with if, and then add a next in cell D3. We already know the function of if. What's the function of next here? Next means to proceed to the next round of loop header and no longer execute the code that has not been executed after it in the loop body. Here, if the code is executed to the next of D3, it means that B4 will be skipped and will not be executed, and the program will directly go to the next loop, that is, it will go back to A2 to judge whether A1 is greater than 1 and decide whether to continue to execute the loop body. Think about this logic process carefully. B1 starts with 2. If A1 can be divisible by 2, output the 2 in C2, divide A1 by 2, and then go back to A2 again to enter the next loop. At this time, B1 is still 2, because next will skip B4, and the statement B1 plus equals 1 is not executed. After all the factors of 2 are calculated, the if of cell B2 will not hold, and then it will enter cell B4 to execute B1 plus equals 1, change B1 into 3, and then enter the next loop. This single-layer loop can achieve the same effect as the above two-layer loop. It should be noted that, if next is used in the looper for n or for AB, the loop variable will still change in the next loop. For example, the previous example of finding the sum of odd numbers can also be written with next. When an even number is encountered, the condition of B2 is established, it will be executed to the next of C2 to enter the next loop, and the loop variable will still be added by 1. When the number is odd, it will be executed to B3 to execute accumulation, and the loop body will be executed 200 times. In multilayer loop, next followed by the name of loop cell can make the outer loop directly enter the next round. For example, the Narcissus number mentioned above can also be written as this. It seems that using next achieves the same effect as break, but the mechanism is different. Next B2 of cell E5 will directly enter the next round of B2 loop, and if it is break, it will jump out of C3 loop. In this example, the effect of the 2 is the same, because there is no code of the B2 loop after the C3 loop ends, and the B2 loop ends too. If the code changes to this, when E5 code is next B2, C6 will not be executed. If it is break, C6 will still be executed. You can try it and understand the difference by yourselves. What happens if you don't write anything after 4, neither the number of loops nor the loop condition? This kind of loop is called unconditional loop, commonly known as endless loop. In theory, this loop will be executed endlessly and never stop, just like goto, which is not used with if. This obviously doesn't make sense. We shouldn't write a program that can't be terminated. However, it's not uncommon to see endless loop code in reality. What's the matter? Because we also have break and if. An endless loop is not really an endless loop, only that when we write a loop statement, we are not sure how to write the end condition of the loop. It needs to be determined during the running process of the loop body. In this case, we will write an endless loop at the beginning of the loop, and use if to judge the end condition of the loop in the loop body. If it is true, we will use break to jump out of the loop. A real endless loop really doesn't make sense. However, if the if used to trigger a break is wrongly written, the pseudo-endless loop may become a real endless loop, which should be paid special attention to when coding. Set a 4-digit number x, split the 4 digits, use these 4 digits to form the largest 4-digit number a, and then form the smallest 4-digit number b. Here, we also consider the numbers that begin with 0 and actually 3 digits, 2 digits or even 1 digit as reasonable 4-digit numbers. Then calculate a minus b to get a new 4-digit number, regard it as x and repeat the process, so that the calculation can be repeated infinitely. If the new x is the same as the previous x in a certain round of calculation, it is obvious that, if the calculation continues, only the same x will appear, and it is meaningless to continue. We call x at this time, digital black hole. Once the number of black hole appears, the operation can be stopped. Section 4. Endless loop. Write a piece of code with endless loop. Randomly choose a 4-digit number x as the starting value, take finding the number of black hole as the ending condition, and output all the x in the process. The initial value is placed in A1. Because we haven't learned the knowledge of set, we can't use the function of set sorting. The most troublesome part of this code is B3 to E7, which is used to sort the 4 digits from large to small. B2 to E2 sort the 4 digits respectively. The maximum and minimum functions are used to calculate the maximum digit in B3 and the minimum digit in E3. D3 is the sum of 3 digits except the maximum digit. Then, B4 to B7 respectively judge which of B2 to E2 is the largest digit. The remaining largest is the second largest digit, which is written in C3, and then subtract it and the smallest from D3 to get the third largest digit, which is written in D3. The final B3 to E3 are the 4 digits from large to small. If we have the knowledge of set, the sorting can be completed in one cell. However, it's good to review the if-else structure again in this troublesome way. The following code is simple. Calculate the maximum and minimum 4-digit number that can be formed respectively, and subtract to get a new x. If it is the same as the previous one, the loop will be ended. Otherwise, the new x will replace the old x to continue the loop. Try it on your own to see if this code can stop and which number can it stop at. Again, if the program does not end due to wrong code, you can use the debugging function to force it to stop. Up to now, we have known several structures to control the flow of program. The first is sequential structure, which is executed from top to bottom. The second is branching structure, which determines the different direction according to the conditions, and will skip some code. The overall direction is still forward. The third is loop structure, which will repeatedly execute a piece of code, including loops formed by goto. If we do not consider the function call, we can say that all programming languages have only such a few process structures. We have learned them all. If we review the examples we have done, we will find that the programming language does not help us find a way to solve the problem. When we encounter a problem, we still need to come up with a solution ourselves, that is, solve the problem through a series of steps using the combination of the above 3 basic structures, which are usually called algorithms. The function of programming language is to provide a way to describe the algorithms that human beings think of, so that the computer can understand and execute. A good programming language can more succinctly describe people's ideas, and programming will be fast. A bad programming language may be very troublesome, and it will be more difficult to think of a solution description than a problem solution. In any case, don't expect programming languages to help us come up with algorithms. If you can't think of an algorithm, there is no solution to the problem.